Hi, welcome back to Musin Chemistry. Today's lesson is Graham's Law of Effusion, Lesson 1. Graham's Law of Effusion states that, and I quote, rates of fusion of gases at the same temperature and pressures are in fact inversely proportional to their square roots of their respective molar masses. Now that's a kind of a lot to say. I mean, really, what does that really mean? Well, first of all, it means this. The rate, let's say, of effusion A divided by the rate of effusion B. Now remember, we're talking about, let's get rid of that double O there. We're talking about an inverse proportion. So what we're going to do is we're going to take the square root of the molar mass of B over the square root of the molar mass of A. And inverse this also means, when we're talking about density, square root of the density of B over the square root of the density of A. And we can use the density stuff later. So we're just going to kind of do a simple problem. So let's write a problem. Let's say the problem is going to go like this. Compare the rates of effusion of hydrogen and, let's say, nitrogen gases at the same temperature and pressure. All right, what do we know about hydrogen and nitrogen? Well, hydrogen has a molar mass of 1.01 grams per mole. And nitrogen also has a molar mass of 14.01 grams per mole. But wait a minute. Hydrogen is diatomic. So there's actually going to be, let's erase this here. Hydrogen is actually going to have double that amount. And so is nitrogen. So since hydrogen is diatomic, which means it's with itself, that would mean that the molar mass of hydrogen is actually 2.02 grams per mole in diatomic form. And nitrogen would be 28.02 grams per mole in its diatomic form. All right, so let's go ahead and let's write this problem. So we're going to put the lighter gas on top. So the rate of effusion, the gas hydrogen goes on top. And the rate of effusion nitrogen on the bottom, which means the inverse proportional means that the molar mass of nitrogen is going to go on top, which is, let's cut it down, let's just call it 28. Over the rate of hydrogen, its inverse square root, so that's going to be 2. So basically we're going to combine these under one gigantic radical, and we're going to go as 28 divided by 2. All right, so basically this would give me the square root of 14 over 1, which equals, let's see here, let's take the square root of 14 real quickly. Square root of 14, it's going to give me 3.74. So since hydrogen's the lighter gas, it makes sense. Let's make that a better looking 4 because I don't like that 4. Hydrogen's the lighter gas, right? So it's going to travel faster. So hydrogen's going to travel 3.74 times faster than nitrogen. So hydrogen is 3.74 times faster than nitrogen. So we'll put a hydrogen there. So for every one that nitrogen makes, for every distance one it makes, wherever that distance is, that would be nitrogen's distance. Hydrogen will have gone 3.74 times further, because it's that much faster. Or you can think about this. If nitrogen and hydrogen were in a foot race, nitrogen is 3.74 times slower than hydrogen. So hydrogen would easily cross the finish line first. No matter how you look at it, it's just that hydrogen's a faster moving gas. So you guys have an awesome day, and we'll see you again on Moose and Chemistry.